Assalamualaikum and a very good morning to everyone, especially to Dr. Zamali. Before we start our presentation, we will introduce ourselves.
My name is Adini Sofia binti Yusuf Sukri. My name is Jasmine Isaina Isabella binti Lamawi.
My name is Hanis Hawani binti Muhammad Ismaili.
Today, we will explain the concept of mechanics, specifically how an object remains in static equilibrium when it placed on an inclined plane or a slope. Mechanics is an important branch of physics because it explains many activities and situations that we encounter in our daily life. When an object is racing on a slope, it is difficult to analyze the forces using the normal horizontal and vertical direction alone. Therefore, we use vector resolution to split the object's weight into two perpendicular components using basic trigonometry. One component acts parallel to the slope, while the other acts perpendicular to the slope. After resolving the forces, we apply Newton's first law, which states that an object remains at the rest when the resultant force acting on it is zero. This means the sum of the forces along both axes must satisfy. Total Fx equals zero and total Fy equals zero. In this presentation, we will explain how physics concepts and mathematical calculations work together to analyze the forces and determine the conditions required for complete static equilibrium.
Alright, moving to the core discussion of our presentation. We want to look at a very specific and practical application of physics in the engineering industry, which focuses on the resolution of forces and static equilibrium. According to the scenario outlined on the slide, we have a mechanical engineering team tasked with installing a massive industrial air conditioning unit. Now, this isn't your typical home air conditioner. This is a heavy-duty unit weighing exactly 1500 newtons. To make things more challenging, it is being installed on a factory roof that is tilted at a significant angle of 30 degrees from the horizontal ground. If we visually analyze the diagram provided here, this grey block represents our 1500 Newton load sitting on the incline. In physics, when an object is placed on a tilted surface, its weight doesn't just act in one simple direction. Because of the 30-degree angle, the gravitational force is actually resolved into two distinct components. One component pressed directly perpendicular into the roof, while the other component acts parallel to the slope, constantly trying to pull the entire unit downwards. Without any intervention, gravity would cause the unit to slide down, creating a major safety hazard. To mitigate this risk and ensure absolute safety during installation, a technician has attached a safety cable, which you can see represented by this line running parallel to the roof's incline. The primary function of this cable is to exert an opposing pulling force, known as tension. By strategically introducing this tension, we are effectively counteracting the downward gravitational force. This creates a state of static equilibrium where the net force acting on the object becomes zero, ensuring the unit remains completely stationary and secure. Now that we fully understand the physical dynamics of the setup, let's move on to the next slide, where we will break down the mathematical equations to calculate the exact amount of tension required.
Now, I will explain the calculation part. The first question asks to find the magnitude of the tension force T required in the cable to keep the unit completely static in equilibrium. To solve any system in statics, we must first isolate our object of interest, the aircon unit, and treat it as a particle system. We do this by constructing a free body diagram. There are three distinct physical forces acting on it. First, we have weight, which is W, the force of gravity pulling the unit straight down toward the center of the earth, and the value of W is equal to 1500 Newton. Second, we have normal force, which is R, the pushback from the roof, because a normal force must act at a perfect 90-degree angle to a surface. Since the roof is tilted, this force points up and away at an angle. Third, we have tension T, the pull from the safety cable acting parallel to the surface of the roof, holding the unit back from sliding down. Then, to construct a free body diagram, we must rotate our coordinate framework to clockwise. Because the technician wants the aircon unit to be completely static, we apply Newton's first law that tells us that the net force in every direction must balance out to exactly zero, where total F is equals to 0. First, let's look at the parallel direction, which we have assigned as our x-axis. Along this axis, we have the tension of the safety cable T pulling up the slope, opposing the component of gravity pulling the unit down the slope. We write our equilibrium equation to T minus W sin theta equals to 0. By moving the weight component to the right side of the equation, we isolate our tension where we get T equals to W sin theta. Then, we substitute all the known values and we can get T equals to 750 Newton. This tells us that the safety cable experienced a constant pulling force of exactly 750 newtons just to keep the unit from accelerating down the roof. The second question asks to determine the normal force R exerted by the roof surface on the unit. Now, let's examine the perpendicular direction, our y-axis. Here, the normal reaction force of the roof R pushes outward, opposing the gravitational force pressing the unit into the deck. Applying our second equilibrium condition, where total F perpendicular equals to 0, our equation becomes R minus W cos theta equals to 0. Just like before, we isolate R by shifting the weight component over, then we can get R equals to W cos theta. Now, substituting our known values, then we can get R equals to 1299.04 Newton. This proves that the roof structure directly beneath the unit must be structurally reinforced to bear a localized perpendicular crushing force of 1299.04 newtons. With both calculations complete, let us now move forward to look at what these numbers mean for our final safety conclusions.
So, in conclusion, by the end of the lesson, students should understand how the concept of mechanics, vector resolutions, and Newton's first law are applied to solve problems involving static equilibrium on an inclined plane. These concepts are not only important in physics and mathematics, but are also widely used in real-life engineering and constructions. For example, if you were a site safety supervisor, this calculation will help you make important safety decisions. First, for cable selection, you cannot simply use any rope. You must choose a steel safety cable that can safely withstand a minimum tension of 250 Newton to prevent it from breaking. Second, for structural integrity, the roof structure does not support the entire 1,500 Newton weight directly. Instead, it only need to withstand the 1,299 Newton perpendicular force acting on the surface. This information helps engineers design structures that are both safe and efficient. Overall, this topic demonstrates how mathematics and physics work together to solve practical engineering problems and ensure safety in a real-world application. Thank you.
That's all from us. Thank you.